Okay, so what we're going to do on the exam, we'll be sending you a message inside web courses through the inbox messaging system that has a list of items on the exam that you got incorrect. And then we'll also publish a little spec sheet, kind of like a blurb sheet, that gives you the gist of each of the questions on the exam. So it'll be equivalent to the exam printout and the blurb sheet you had from exams 2 and exam 1. All right. And unfortunately, it used to be in the old web courses, which was based on Blackboard, we could configure the exam so that you could look at the feedback. You know, you guys may have noticed that a lot of the questions in our homework and stuff, they have a little feedback thing, and it refers to like the old textbook and stuff that we used to use. And those are older questions from when we had Blackboard, and you can still reuse the questions, but you can't really edit that stuff, and you can't activate a test so that you can see the feedback but not the verbatim question, you know. And so, we can't do that in Canvas, but we're going to get you the information, the equivalent of that. Chop, chop. Questions about exam 3 before we continue with the spectrum of hydrogen. Yes? Before you leave for summer? Wait a minute, that's right. Summer vacation's coming up pretty soon. Man, it has been so fast. Frankie, I usually don't have time to put your grades in web courses because I have so many students and it takes so much time getting it all cleaned up and rounded up and wrangled that by the time the deadline for grades comes, I get it in right at the buzzer and then I go home and collapse. And I don't have time to get the grades in, but maybe I'll try this semester. But you'll be able to figure out, because you'll be able to see your exam grade, your final grade. And also, since we've done 3 midterms now, and most everybody in here has taken all 3, you have all 3 exam grades, now I'll be able to put best 2 out of 3. All right? Also, I'm going to try to put up maybe tomorrow, a clicking pointage roundup as of today. And then from that, and getting your homework pointage is fairly easy. You should be able to kind of work it out yourself. If you come to office hours, I'll work it out for you or with you, show you how to do it. And it's normal. I do that every semester, last 3-4 weeks of the semester, everybody's starting to get nervous about grades and stuff. So yeah, you should be able to figure it out, even though a formal A, B, C, D, or E, or A, B, C, D, or F might not show up in web courses. Okay, because web courses, Canvas, I have a lot of, emotions concerning. Don't put this in the Twitter feed. But I have a lot of hatred for for Canvas, and one of the things is that the Dipsy grading mechanism they have built in that sucks. It's just as bad. Especially for me, I try to have a grading system that's good and that challenges the students, but it's not simple. So, did you have a question? Yeah, your grade, yeah. Yeah, it'll be, I know those of you that hopefully are graduating and not going through the UCF you can't finish mode, which seems to be the fundamental mode of the entire university. If you come to office hours or message me in web courses, inbox messaging, we can kind of eyeball it. Right, but I'll be working on that the next week. So we only have a few more lectures, so we got to make it count. Another question before we continue. All right. Now, I want to give you some more comments and instruction about the spectrum of hydrogen. And actually, what we'll do is we'll start with the continuous spectrum. The 4 wavelengths that we viewed are in what we call the visible band, or the Roy G. Biv band. And Roy G. Biv, you know, the physics joke is that there's a famous scientist named Roy G. Biv, and when he died, you know, instead of donating his body to science, he donated his name to science, because his name is the exact sequence of the colors starting from red and going all the way to violet in the visible band. Roy, red, orange, yellow, G, and middle initial. I wonder what his middle name was. He probably had a really cool middle name. And then Biv, blue, indigo, violet. All right, so that's this list here, Roy G. Biv. Okay, and those are just kind of informal classifications. The visible band, you know, when we think of a rainbow, we think of this band. But in actuality, the sun produces a lot of infrared, a lot of ultraviolet. Ultraviolet is what produces sunburn. So, all right. Now, what we just saw was this spectrum up here. Can you turn the lights all the way off just for a second? All right. I want you to eyeball this picture. All right. Just for a second. Here's H alpha. Now, on the YouTube, it's going to be a lot brighter. All right. And here's H beta, the kind of tealish line. And here are the really faint purpley ones. They're called H gamma and H delta. Now, in this diagram, it goes left to right. All right? And here, go ahead with the presentation mode. Okay? Here are the different wavelengths. H alpha, 656 nanometers. And remember, a nanometer is 10 to the 9th of a meter, a billionth of a meter. So pretty small. A millionth of a millimeter. And dear, a millimeter is pretty small. Just take a millionth of that, and that's a nanometer. H beta, the aqua kind of tealish second line, second brightest. 486 nanometers. H gamma, 434. We're getting shorter and shorter. And H delta, 410 nanometers. Now, the informal breadth of the visible band is from 400 to 700. Okay, so violet is down at the 400 level. And that's where we find H delta and H gamma. 410 for H delta, 434 for H gamma. And then 700 for the red end, okay? And we see that our H alpha wavelength, 656, is getting up there towards the top. Now, this is kind of an informal range. You know, there might be, you know, individuals in this room that can make out 395. You know, deeper violet than the violet. Okay, there may be individuals in this room that can make out 703, all right, or 710. And that's even redder than the reddest red that everybody else can see. They say that insects that have infrared or can see in the infrared band. Well, we can't. All right, this is our visible band. So anyways, this is called the Balmer series for hydrogen, a series of 4 visible lines, and they're pretty important. Now, there is a pattern in this set of wavelengths. It might not look like it. 656, 486, 434, 410 in the nanometers. There is rhyme and reason to that. It doesn't look like it when you just look at it at the first glance, but there is a pattern, and the wavelength pattern, let's go to the next slide. It's kind of tricky. Here's the listing again. And by the way, over here in the third column is the frequency in terahertz. All right. And so 450 terahertz, 457 for H alpha, and so on down the list. Now, the pattern in wavelengths, you know, there's a pattern in frequencies, but it's easier to do the pattern in wavelengths. All right, and the guy that figured it out is Dr. Balmer. And he was a mathematician, but in his day, in the late 1800s, you know, mathematicians were very, you know, up on physics and chemistry. Chemists were up on math. Unlike today, where it's so highly specialized, there's parts of physics I don't even know. You know, I know all about relativity and astrophysics and stuff like that. But other stuff, you know, like silicon, you know, solid state semiconductors, clueless. Astronomy, and Darian's over here, yeah, he's clueless. Anyways, Johann Balmer figured out the guys that rendered an explanation for it, a theory for it, were Einstein and Bohr. Now, Bohr, I think we've mentioned before, his first name is Niels, 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 from Denmark. Pretty smart guy. And he and Einstein figured out the quantum theory, or the beginning of the quantum theory of hydrogen. Now, a couple things about the Balmer series I want to point out. Here's the series again. It's actually fairly easy to figure out the wavelength. If I took 20 of you into a lab and we had some lasers and we had some rulers, some meter sticks, and you know, like a few staplers filled with staples, you could use a block of staples, believe it or not, open up the stapler, take out a block of staples, regular spacing, and use that like as a diffraction grating. And you could get the laser beam to spread out into certain positions. And you do all the trig, you know, you measure the distance from the laser beam to your diffraction grating, and then you know the spacing of the lines on your diffraction grating, and it's printed on this. By the way, send your diffraction gratings to the aisle, please. And Darian, could you collect? Send your diffraction gratings over to the aisle. And so if you analyze the trig and you measure the distances, you know, look at that angle theta, you know, and you can't really do it with just the diffraction grating. But if you were in a lab and you could pace off the distances and measure the distance over to the left or to the right, you could figure out the angles. And once you get that, you can figure out the wavelength. And make a note. Item Roman numeral 4, yeah, using constructive interference. Because up here, where you see H alpha, and down here, C is the central image. And the red H alpha line is, you know, some number of degrees over here to the left. And here's your eye down here on the far left. Okay, so you're looking at this, and you look straight into the central image, C, and then off to the left, you see the H alpha line. You can measure that angle in the lab. And we can't do it here because we don't have meter sticks and stuff like that, but it's not that hard. And then if you apply the idea of constructive interference, you can figure out, okay, that means that a simple trig calculation lets you figure out the wavelength that produces H alpha, or the wavelength of H alpha, right? Now, I mentioned that there's a pattern, thank you, dear, in the Balmer series. Now, I'm going to give you a bodacious formula, and this bodacious formula you're going to have on homework, all right? All right, so pay careful attention. We're going to calculate with this formula. Here it is, the Balmer series for hydrogen. 1 over lambda equals a constant called the Rydberg constant times this bracket, 1 over 2 squared minus 1 over n squared. And n, for the Balmer series, can have values 3, 4, 5, or 6. All right? Now, the guy that figured, I have no idea how he did it, but Johann Balmer is the one that figured this out. And he's screwing around. He knew that there was this, there had to be a pattern. There had to be some kind of mathematical structure, just like Galileo said. You know, Galileo said that the book of the universe is written in the language of mathematics. And Balmer was a mathematician, so he said, all right, this is part of the universe, these diffraction lines that we're looking at. You know, the chemists, you know, they're sitting around, you know, doing electrolysis of water to separate oxygen and hydrogen. It's easy as walking through the park. So they have nice pure hydrogen. They zap it like we did with some high voltage. They could do that in the 1880s. And then look at it through a diffraction grating or through a prism. You know, prism will do too. And measure the wavelengths. And Balmer said, this is the pattern. Take the inverse of the wavelength and then multiply 1 over 2 squared minus 1 over some number squared and multiply by this constant r, and bing, you have the wavelength. All right? Now, here's the Balmer series. It all fits. H alpha, H beta, H gamma, H delta. All right, so n equals 3, that gives you the wavelength for H alpha. N equals 4 will give you the wavelength for H beta. And we're going to calculate that right now. So let's try verifying Balmer's formula for n equals 4. Here we go. All right, so let's set it up. And so here it is, except instead of n, I have 4. We're doing it for n equals 4. So it's 1 over lambda equals blah-de-blah. And this is, Rydberg's constant is something that you can measure in the lab. Works out to 1.0974 times 10 to the 7 meters to the minus 1. Bloop! What is that? Well, like many of the constants of nature, Robert, right? It's weird. Inverse meters. Well, if you look at this formula carefully, you'll see that in the square brackets, there's no units. Okay? In the left side of the equation, 1 over lambda, that's going to be 1 over a distance. So that's going to be 1 over meters, or meters to the minus 1. So the Rydberg constant, it's got to be, you know, meters to the minus 1. Some number of meters to the minus 1. All right? Now, let's do that fraction inside the square brackets. And for those of you a little rusty with your fractions, here we go. All right? 1 over 2 squared, that's 1/4. 1 over 4 squared, that's 1/16. All right? Common denominators, 16ths. So 1 over 4 is equal to 4 over 16. And then I already have 1 over 16 over here, and a minus sign in between them. So these square brackets, kind of yucky looking. And if you're doing some higher value of n, you know, it might be a little tricky. You might have to use, you know, like, I don't know, 64ths or 72th fractions or something. But, I mean, you could do them. In this case, you use 16th fractions. That square bracket comes out to 3/16. All right? So you put that back into the formula. All right, let me get that scratch work out of the way. Here it is. So 1 over lambda, okay, here's the Rydberg constant, 1.0974 times 10 to the 7 inverse meters, times my square bracket, 3 over 16. Ding! All right, so if you can do a fraction in the square brackets, subtraction of 2 fractions, you can handle Balmer's formula. You know, it's not too bodacious. But this is the formula for 1 over lambda. So you have to inverse to get lambda itself. Write that down in your notes. This is the formula for the inverse wavelength, 1 over lambda. To get lambda itself, which is what you're trying to get, you do this result here, and then you go 1 over it. Right? You invert this. So I'm going to invert the formula before I calculate. You can calculate here this stuff, you know, 1.0974 times 10 to the 7 times 3 divided by 16. and then hit the 1 over button on your calculator, perfectly fine, if you know what you're doing. Or you can do it this way. And just invert it. Okay, so here's your inverted. Right, down here in little letters, down here on the left in the middle of the screen is the formula for 1 over lambda. Here's the inverse of that. And now I have 16 in the numerator and 3 in the denominator. And down in the denominator, I have the Rydberg constant. So it's kind of messy looking, but it's not too bodacious. And you guys are bold scientific students now, so you guys are, you know what? I'll just say this before the end of the semester, and you can call home and tell your mom and dad. You guys are, I'm very happy with your work this semester. Almost everybody in here, I'm not going to look, I know there's a few that haven't, but almost everybody in here has worked really hard to do well. And I really, I treasure that. Okay? Now there's a few people that aren't here that haven't worked hard. And, well, I'll just be nice and not point out anybody that I know is, yeah, there's a few slackers in here, but they're not here today. So, but anyways, in general, I love having this class. I love seeing you guys get more and more confident. And I love seeing you work hard and think. And I've been very happy about it. I just, so my hat's off to every single one in here. And I don't want anybody in here to ever say, even the people I had to yell at like at the first day of classes, I don't want anybody in here to say, I stink at science. That was maybe true, 4 months ago, but that was then. This is now. You guys are doing great. All right? Anyways, let's get down to business here. All right, so here we go. Now, 3 times 1.0974, go ahead and verify me. That should be 3.2922. Anybody verify that? 3 times 1.0974. You got it? Verify? Who else verifies? Get your calc. Okay, good. Any verification over here on the left side of the room? Okay, Kimmy's going for a calculator. Now we mean business. All right. Now, 16 divided by that, 3.922, that's 4.86. So now I just got to, and by the way, 10 to the 7 in the denominator is 10 to the minus 7 in the numerator. All right? And then meters to the minus 1 in the denominator is now meters to the regular 1, or just meters, in the numerator. So we're looking good. All right? And so 16 over 3.2922 is approximately 4.86. And then I have 10 to the minus 7 meters. And that is looking good because if I now convert that to 10 to the minus 9 and move the decimal point 2 spaces over to the right, I get 486 times 10 to the minus 9 meters. And my wonderful students, that checks. 486 nanometers for H beta. N equals 4, yep, this is how it works. Now the guy that figured this out is Balmer, and there's a whole bunch of other series in infrared and ultraviolet. Matter of fact, astronomers use something called the Lyman alpha, which I believe Lyman alpha is in ultraviolet. And they actually use that to probe the depths of the universe as far back to the Big Bang as possible by analyzing the Lyman alpha from all the hydrogen in the early universe that's just getting to Earth right now. In the first a few billion years of, or first few million years, I should say, of the universe. Hydrogen was cooking and sending light, but it was so far away from us that it's taken 4-point-something billion years to get to Earth. And it's gone past galaxies and clusters of galaxies and black holes and everything. And when you analyze the Lyman alpha line, you can, make out a lot of the features of everything between us and the source. So Lyman alpha, that's in the Lyman series. And there's a bunch of other series as well. But this is the Balmer series. Here's kind of your summary. And down here in the lower left, this yellow box, this is the thing that we want to focus on. The fact that there is a pattern means that there's got to be some unseen regularity inside the hydrogen atom itself. In other words, this is not a coincidence. Now, we're pretty sure, they were pretty sure at the time that it wasn't F equals ma. Of course, everything boils down to F equals ma, but with atoms and stuff, it's really hard to work with F equals ma. But energy levels, yeah, baby. Energy levels is the way to go. And angular momentum, oh, you can get it all by analyzing energies. Okay, and by looking at the alpha wavelength, 656 nanometers, and all the others, you can figure out something that's important. And what's important is these visible wavelengths, H alpha, H beta, H gamma, H delta, and all the other series, they're like the fingerprints of hydrogen. Whenever we look at a star far across the universe, far across the galaxy, and we put the starlight through a diffraction grating, if we see these visible lines like this, we know, yep, there's a lot of hydrogen in that star. And that is how we know a very, very basic fact of the universe. And you can write this down. 74% of the visible universe is hydrogen. And we know that because we can spot its fingerprints in the Balmer series and in the other spectral series for hydrogen, like the Lyman series. Let me repeat that. 74% of the visible universe is hydrogen. And about 25% in there of the visible universe is helium. Now, helium, make a side note, helium has a completely different discrete spectrum. And usually I do hydrogen and helium together, because helium makes up about 25% of the visible universe. And the other, like 1-point-something% is all the carbon in your body, all the nitrogen that you're breathing, all the oxygen that you're breathing, all the iron in the steel in your chair and in your car, all the silicon in your computer, your phone, your watch, whatever you have, all the silicon in every glass that you have for drinking water at home, all the carbon in your gas tank. Those are hydrocarbons that power your car. Those are in like the last 1-point-something% of the visible universe. If you have a wedding ring or any kind of jewelry that's got gold, yeah, that's a very teeny fraction of that remaining 1%. Magnesium, aluminum. If you have a bike that's got aluminum wheels, yeah, that's inside. Most of the universe, it's unbelievable. It's 3-to-1, hydrogen to helium, and then a little bit left for uranium, silver and gold, copper, iron, all that stuff. Now here on Earth, the proportions are a little different. But in the universe at large, yeah, it's mostly this. Matter of fact, our star, this is a picture of the sun spectrum. Now take a look at this. Eyeball this one, you guys. Take a look at it. Okay? Eyeballs. Eyeballs front. This one is a rainbow, and there are colors missing. Right? See those little black, it's like a gap in somebody's smile, between their two front teeth. But the sun's got a lot of gaps. And those are what we call absorption lines. They tell us that there are certain elements that are absorbing specific colors. All right? They're in the surface of the sun or in the gas around the atmosphere around the sun, and they're not emitting, they're absorbing specific colors. These are called absorption features. And hydrogen, we can see hydrogen absorption features. Let's see, beta would be up in here somewhere, up in these greenish blues. H alpha would be down here if it's absorbing. All right, so all these gaps, they stand for different elements. Yeah, we see different elements, not very abundant, but yeah, we can see all kinds of different elements like sodium, nitrogen, carbon in the atmosphere and in the surface of the sun. And by the way, helium, the element, was discovered here. There were gaps, spectral line gaps, spectral line absorption features here that they couldn't figure out where it came from. Who ordered that? It wasn't hydrogen, it wasn't oxygen, carbon, nitrogen. And they knew all that stuff. They didn't. What is this element? So you know what? They said, okay, it's got to be an element. We'll call it helium, after Helios, the sun. That's where they discovered it. And then later on, they discovered it in natural gas coming up from the, underneath the ground of the earth. So the helium that you get in helium balloons at the store is abundant in the sun, pretty rare here on Earth. But they discovered it in the surface of the sun. All right, let's talk about the quantum structure of the hydrogen atom. Here we go. All right, now we got a good half hour almost for this. So let's crank on this. Here's what we know. Here's what we figure is happening. And we mentioned this last time. Only a few orbital levels are allowed. An electron only live at specific orbital altitudes. So you can think of it as, a matter of fact, it's kind of like, air traffic controllers. Anybody in the room here know an air traffic control? Do you? Do they? Your dad does that?
No, my friend mom.
And do they keep certain sets of planes at different? They keep them at certain altitudes, right? I mean, when they're getting close to the airport. In fact, all the way, I think, all the way on their routes, they assign them an altitude, and that's where they're supposed to stay. Okay, and the same thing with but each altitude above the nucleus has a certain electrical potential energy. Now we went through the list of that. 13.6, negative 13.6 for n equals 1, so on. So the quantum theory is that there are countable energy levels, and only those energies are allowed for electrons in orbit around the proton. Right? And then the second part of the theory is that when an electron bumps downward, for instance, from n equals 3 to n equals 2, it emits a photon of light, right? For n equals 3 down to n equals 2, guess what, guys? That's the H alpha transition. So when an electron dips down to a lower orbit, it's nice, changes in the electrical potential energy, that missing energy goes into the H alpha photon, and that goes zapping out somewhere else in the universe. So you number the orbits, and as the electron drops to lower EPE, it emits a photon with the missing energy. I want you to read in chapter 9.6 about photon energies being quantified and quantized, and countable atomic energy levels. Here's the formula that these guys used for hydrogen. That's a picture of Niels Bohr and Albert Einstein kind of chilling out at some scientific conference, probably talking about electrons or something. Or maybe talking about what's for lunch, who knows. Anyways, that's the two guys. And they kind of worked out the basic quantum theory of hydrogen. In other words, the energy levels. When you drop an energy level, the energy goes into the photon. And here is where Planck's constant H comes into play. The energy of the photon is equal to the Planck's constant times the frequency of the photon. E equals hf. Now, we'll do a simple calculation with this on Tuesday next week, I think. But go ahead and jot that down. The reason that Planck's constant came in here is the following. E equals hf. Planck is the one that came up with this formula. He was thinking about incandescent lights, the source of thermal radiation. And the observations, they couldn't figure out a form, like Balmer figured out a formula that worked pretty good for hydrogen, visible. But nobody could figure out the rule, the theory, the formula for incandescent light, just a thermal light source. Hydrogen, yeah, Balmer nailed it. Hydrogen ultraviolet, yeah, somebody else nailed that. Hydrogen infrared, yeah, somebody else nailed that. But nobody could figure out incandescent thermal light sources until Planck. So here's what Planck said. He said, all right, the electromagnetic field, the source of that, is a wiggling electron somewhere, or a wiggling proton, an oscillating or accelerating charge, either positive or negative. That means it sends out a pulse of those field lines. Basically, it says the field lines wiggle. And also, because it's electromagnetic, there's an electric field lines that wiggle, and perpendicular there. And perpendicular to that are the magnetic field lines, okay, which we didn't sketch out. We could have if we wanted to. And everybody knew in the late 1800s, that oscillating charges would produce electromagnetic waves. They were able to do that. Matter of fact, the first person that did it was Professor Hertz, Heinrich Hertz. And that's why the unit of frequency is named after him, the Hertz. He generated accelerating, oscillating electric charges and measured the electromagnetic wave from that. He created waves. They've since figured out that light itself is an electromagnetic wave. So Planck said, all right, if we have an incandescent light source, it's got to be the fact that there's electrons and stuff that are oscillating in the surface of that hot object at all different kinds of energies and emitting light. Now, what he found was, and everybody else was thinking about that, but they couldn't explain the exact distribution of energy in the spectrum of the incandescent light until Planck said that, well, let's go into this outline here. He said that the only way that this is going to work is if every oscillator can have only certain energies controlled by its frequency. Now, if you are an electron, you can accelerate an electron at any acceleration, pretty much, that you want. And when it does that, it generates electricity. But Max Planck said, if it's in a thermal system that's emitting light because it's hot, the frequency of those oscillations controls the energy of the light that is generated. And the energy is E equals HF. Now, he's the one that figured that out for about the year 1899, 1900. So this is a few years before Einstein and Niels Bohr, about 10 years or so before those two cats. Okay? And he said, look, if you've got something hot, the distribution of light, that rainbow, some colors are brighter than others. Green, for instance, for the sun. The sun has the perfect temperature for which the brightest, the most energy is coming. Guess what color which color of the spectrum carries most energy toward Earth? We got red, orange, yellow, green, blue, indigo, and violet from the sun. And so a lot of energy is coming through each of those colors. Which color? As a matter of fact, let's do a question. Turn on your clickers. And let's do a short answer question. Okay. And I want you to type in the color. And so hit your refresh key. Okay. And type in the color. Or if you just want the letter. ROYGBIV. Of the Roy G. Biv colors, which one do you think carries the most energy? Is red, orange, yellow, blue, indigo, green, blue, Roy G. Biv? Which of the Roy G. Bivs? One of them is measurable. Listen to those clicks. Now, everybody's going to get a point for this, okay, because this is kind of a educated guess. But I want to see what you guys, some of you are typing in words, good. Some of you are typing in letters, good. Who typed in the letter P? Purple, no, violet. If you typed one person, if you typed in P, go back and change it to either B, maybe that's what you meant, or R or V or whatever it was you meant. Okay. Okay, I can see people voting for different colors here. All right, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Boy, you're all over the place here. Well, that's good, though. Oh, wait a minute. Look, bring it down. Okay, let's take a look at this. Clearly, Derek, can you see if this will sort by... No. Compare? No. Answer. No. Okay, this one doesn't show yet. Let's go down. All right, let's go to the top. There's a lot of reds, a lot of people voting for reds. But my wonderful students, you know what the most abundant energy band is? Maybe this will make sense to you. It's green. You voted for green. That's it. Isn't that amazing? Do you think it's a coincidence that plants, almost all the plants in the world, are green? And why is it? Why is a plant green? You look at it and it's green. You know why? Because it reflects more green light to you. It's actually reflecting more green light than any other color. So it's not absorbing the most abundant energy, it's reflecting it. Think about that for a minute. If you think about evolution, what's the I don't even know the answer to that. You probably think about it. You're the biologist. What's the evolutionary advantage of reflecting green, of not using it, and using everything but green?
I don't know what the evolutionary advantage of. I know that some plants do differ with that.
Right.
Though.
Some use different colors. Yeah, that's right. But green is the most. So it's kind of cool. And here's another interesting thing: water. The same everywhere in the universe, H2O. But guess what color is that water is most transparent to? Green. Water is it lets green in the best. What is your eye made of? The inside of your eye, that vitreous, what do they call it? The aqueous stuff inside your eye? It's water. Isn't that cool? Your eye is exactly adapted to the most abundant light from the sun because it's made with water. It's interesting. All right, anyways, Einstein said, all right, this works. Planck said, okay, I got it. I got thermal light sources. If all those little electrons emit only energies, depending not on how big the amplitude is, but how big their frequency is, they could, because the electrons might go by 1 nanometer or half a nanometer of oscillation or a tenth of a nanometer. But forget about the size of the amplitude of their oscillation. Just give me the frequency, and that's going to be the frequency of the light and the energy of the light according to this formula. And then Einstein said, yeah, let's take that same formula and supply it to the hydrogen atom. Specific size hunks of energy, and each of those go into a photon of light. And by God, it worked. They figured out, they could, if they eventually figured out the mass of the proton, the mass of the electron, and they were able to figure out, okay, now, what are the orbital sizes, and we know the energies, we know the wavelengths and stuff, and it all works out. It all fits perfectly with E equals HF, Planck's relation. But here's the problem. Why is it that only certain, and write this sentence down. Darian, you can grade that now. Why is it that only certain energies are allowed? Einstein and Bohr said, okay, we've got these energy levels, and they're perfectly explained by the color of light, by the proton charge, the mass of the proton, electron charge, the mass of the electron. It all works out. But why are those the specific altitudes? Nobody figured that out. They said, oh, well, there appear to be specific altitudes, but why are those altitudes chosen? The guy that figured that out was a French guy named Louis de Broglie. And he used Planck's constant equals HF for electrons. And we're going to do that in just a minute. Here's my favorite slide. Planck's constant, the one constant to rule them all. And here's the value of Planck's constant. And I think in homework next week we'll do a calculation. 1 or 2 Cinci calculations with this. And actually what I think I'll do is give you this in electron volt seconds. It's a little easier to do in electron volt seconds than joule seconds. That's called the quantum of action, H, Planck's constant. And it is the thing that rules the hydrogen atom and every atom, every physical interaction in the universe is involved with Planck's constant. So why is there this granularity? Why are you don't get a grayscale variation from one orbit to the next. You either get, it's like my way or the highway. It's either n equals 2 or n equals 3, and you don't get an n equals 2.5. It's like, how they say close only counts with horseshoes? Yeah, same thing here in the atom. It's either n equals 2 or n equals 3 or one of the other integers. But no fractions. Right? The guy that figured it out was Louis de Broglie. Here's a picture of him. French guy. And this is in the early 1920s, right after World War I. And everybody's studying the atom. Big hot topic. Lots of people, Einstein racking his brain, Niels Bohr racking his brain, Max Planck, he was still in the game, racking his brain. Everybody's racking their brains. why are these orbits where they are? And Louis de Broglie said simply this: treat the electron as if it is a wave. All right, now I want to talk to you about this supposition. The supposition was that the electron was a particle. Now, a particle is like a baseball. It has a specific position, up on its orbit, has specific, properties, mass, specific dynamical quantities, kinetic energy, momentum, specific positions, no problem. But a wave is definitely not like a particle. So make a note, a wave and a particle seem mutually exclusive. A wave diffracts. Particles don't diffract. Particles don't interfere with each other. They'll collide, yeah. They'll interact, but they won't, have constructive interference. Baseballs don't do that. BBs don't do that. You drop a water balloon from the top of the library, it's not going to diffract. It's going to accelerate, yeah. Waves can accelerate. They can change speeds. That's how your lens works. It changes its speed as it goes from air into glass. But particles, so here's your problem. If I say that an electron is a particle, and if I say that an electron is a wave, am I crazy? Or is that really the way the universe works? Here's another illustration that I like to use. If you think about a particle is very easily organized. Okay? It's an object that can carry certain quantities, certain physical and dynamical quantities. It can carry a mass. It can be assigned a mass. It can be assigned a kinetic energy and a momentum, an angular momentum, positions, temporal spacing, elapsed times. Everything's nice for a particle. Particles like a bookshelf. You put stuff up on the third shelf, second shelf, books are in there or they're out. Everything's squared away. Everything's copacetic. But a particle and a wave are about as close to each other, as consistent with each other, as a bookcase that is also a horse. So there's your phrase. The bookcase that is also a horse. And think of a horse. Raise your hand if you've ever ridden a horse. It's lovely, isn't it? Well, it's exciting, except if you get saddle sores, but it's fun. And a horse is this beautiful animal, and it can gallop and appear ghostly through the meadows and, in the misty dawn of time and all this, and a bookcase is boring. You buy it at the furniture store. You buy it at Walmart, but a horse, it's a living creature. So saying that a particle is a wave is like saying that you have a bookcase that is also a horse. Now, you wouldn't say that about a bookcase and a horse, but that's what we're saying about the electron. And here's how it works. I don't think you'll be able to draw this picture, but I want you to look at it. He said, if you think of the electron as a wave that is going around in orbit, and if it only has orbits in which the wavelength is exactly the right size to have constructive interference, okay, just like, with Darian over here, when we did the demonstration, Darian and Caroline, at a certain frequency, they got a standing wave. Other than that, they couldn't quite get it. The same thing here. Certain orbital sizes, certain energies, certain frequencies, and only at those do you get constructive interference. And that is how de Broglie said that electrons have got to work. And we know it's true on a guitar. You know, a guitar string, only certain frequencies. So there's not, you know, the fact that you say, oh, only certain things are allowed, only certain frequencies, only certain wavelengths, yeah, that's not so surprising. But to say that an electron is not just a particle, it's also a wave, and at the same time, that, my wonderful students, is kind of unusual. Now, here's the formula. This is the Planck, or this is the de Broglie relation. The wavelength of the particle is Planck's constant, h, divided by its p equals mv momentum. Lambda equals h over mv. Okay? So the momentum state controls the size of the wavelength. And all that is controlled by the orbit and the energy. The charge on the electron, the charge on the nucleus, whatever nucleus it happens to be, hydrogen or uranium or anything in between. So let me close today's lecture with this question. If an electron is a particle, how can it also be a wave? Will the electron diffract? Because particles cannot do that. And what we'll talk about on Tuesday next week is electron diffraction and the observations that were made very soon after de Broglie made his hypothesis. Okay, homework 17 over the weekend. You're dismissed. I'll see you next week. Good class today.
I wanted to ask if I can send you the final exam review so I can just take a look over it.